Hi there! For this video, we'll be having more examples on nature of fruits. So I did this video since I think there are some type of examples that I was not able to tackle in the previous one. So just as a recall, if we have ax squared plus bx plus c equals 0, the discriminant d is given by b squared minus 4ac. And we have three cases. There. If d is less than 0, then our roots are 2 imaginary. If d is equal to 0, then we'll have 2 real and equal roots. If d is greater than 0, then we'll have 2 real but distinct roots. So take note of these cases as we will be needing this in answering some examples. Let's have this first example. Let's have 3x squared plus 4d x plus 12 equals 0. And suppose that we are tasked to find when will this have a real and equal root. So how do we get this one? Recall that to have a real and equal root, we must obtain d equals 0. That means we'll have d equals b squared is 4d. So we'll have here 4d squared minus 4 times a is 3. So we got here 3 times c is 12. So we've got here 12. Simplifying, we'll have 4d squared. Quantity 4d squared is 4 times 4 is 16. Then d times d is d squared minus 4 times 3 times 12 is 144. And since we know that this one is equal to 0, then we can apply linear equation. Actually, this is quadratic since we have d squared. So what we'll do is we'll move 144 to the right side to obtain 16d squared equals 144. Then we divide both sides by 16 to obtain d squared equals 144 divided by 16 is 9. Then we get the square root both sides to obtain d equals 3, but don't forget d plus minus. And this is the answer. So basically, if d is equal to positive negative 3, our roots will be real and equal. So that is how this example works. Let's try out a similar one. Let's have a y squared plus 5x minus 7 equals 0. For this time, we are tasked to find when will our roots be imaginary. So basically, we'll find the value of a that would make the roots of this quadratic equation imaginary. Again, for this to be imaginary, d must be less than 0. So let's solve for d. D is equal to b squared, so that is 5 squared minus 4 times a times c is negative 7. So don't forget the negative sign. Negative 7. Simplifying this, we'll have 5 squared is 25. Then negative 4 times a times negative 7 is plus 28a. Then we'll have here less than 0. Since we know that for this discriminant to be, for the roots of this quadratic equation to be imaginary, the discriminant must be less than 0. Solving this inequality, we'll have 25 plus 28a less than 0. Then we move 25 to the right side to obtain 28a is less than negative 25. Then we divide 28 both sides to cancel this one out, and to obtain a is less than negative 25 over 28. And this one out here is the answer. So for all values of a that is less than negative 25 or 28, our quadratic equation will be imaginary. Or the roots will be imaginary, rather. Let's have this final example. Let's have 2z squared minus z minus 2k equals 0. This time we'll determine when will the roots of this quadratic equation be real and distinct. So for this to happen, d must be greater than 0. So we solve for d. D is equal to b squared. Since it's not written here, we know that there must be a 1 out here. So our b must be negative 1. So we've got here negative 1 squared minus 4 times a is 2 times c is negative 2k. Simplifying this, we'll have negative 1 squared is 1. Negative 4 times 2 times negative 2k is plus 16k. And this must be greater than 0. So to solve this one, so we'll have here 1 plus 16k is greater than 0. To solve this, we move this one to the right side. We'll obtain 16k is greater than negative 1. We then divide 16 both sides, cancel this one out, and obtain k is greater than negative 1 over 16. And this one out here is the answer. So for all values of k that is greater than negative 1 or 16, the roots of our quadratic equation will be real and distinct. So that is our exercises for this one. So I hope you enjoyed this video. Feel free to comment down below any comments, suggestions, and recommendations that you have for our future videos. So that's it. Just a short one in this one. And that's all for this video.